Our speaker is Daniël van Eeden, and he's going to introduce you to TiDB, as you can see on your screen. So if anyone's not aware of it, it is a distributed database that's basically compatible with MySQL. And well, I will let Daniël introduce you to TiDB, to himself, and to his talk. So Daniël, best of luck. If anyone has any sort of questions you have, to ask questions in the chat or in the specific Q&A section, and those will be answered after the talk. So good luck, Daniël, and let's begin.
Thank you for the introduction. So today we're going to talk about TiDB, and it's meant to just be a brief introduction for those who are not familiar yet with TiDB. So I'm Daniël van Eeden. I've been working as a technical support engineer for PingCAP now for like about 4 years. Previously, I've been working as a DBA at Booking.com, so I'm quite familiar with like running databases at like large scale setups. So PingCAP, that's the company behind TiDB. So TiDB is the product, PingCAP is the company. And we have a really good open source culture at TiDB. So all the things we do is all on GitHub, both the code, the issues, the pull request. So you can just follow the product on GitHub if you want. The license is the Apache 2 license. So if you want, you can also like make changes and send a pull request. And so the basics about TiDB. The TiDB database platform is an open source MySQL compatible database system. And by rethinking and rewriting the database with scalability in mind, we've created a database that's easily scalable and also high available by default. So we are compatible with the MySQL network protocol and the MySQL syntax. The thing we do not use is any of the MySQL code. So everything is built from scratch, and we are not depending on any MySQL code. So to describe the reason for why we have TiDB in the first place, we need to look at MySQL. So MySQL was created around 1995 for the computer systems that were available at the time, the networks and disks that were available at the time, which were quite different than what we have today, because this was basically pre-cloud, just like the internet was just starting. And MySQL worked really well for like the early internet, and it really allowed the internet to grow and become what it has been today. So it worked really well, but yeah, it started like now quite a while ago. So if we are looking at some of the things that MySQL is used for, and we are trying to like make it high available, like that's one of the things you usually want with like a large website or like an e-commerce setup. So making it high available is one of the first things that's required. So what's being used here is like a single primary with like 3 replicas, as you can see on the picture, and then like the application writes to the primary and reads from the replicas. This all seems to be fine, but there are like a few issues with this whole setup. Like the first thing is that if you like the primary fails, you need to promote a replica, and this is not automated. These are just manual steps, and of course there are ways to automate this, but that's not built into the whole product. And you want to like use a load balancer for discovery, but you have to like send writes to like the primary and reads to the replica. So you need to like figure out what machine has what task. So that's all non-trivial. And like there's no real leadership election. So since then, we have seen newer ways of doing this, like with Galera and with group replication, which is like one of the components of in a DB cluster with MySQL. But the setup most people were using for like a long time is this setup with like a splitting of read and writes, and then adding machines for high availability. So in TiDB, high availability is the default. It's built in, and this is because all components are redundant, and the applications is expected to retry failed connections, but it can always retry a connection to the same set of machines. And the tables are split into smaller parts of around 96 megabytes. We, in the last few releases, changed this to a slightly larger size of 256 megabytes. And these data regions are stored on the TiKV nodes. And because we have multiple copies of everything and multiple machines for every role, things are high available by default, because any component can fail and the cluster can just continue serving data, serving queries. So all the components that make up a TiDB cluster. The first one is the placement driver. Those are usually like 3 nodes, which is a rough group for like leadership election. There's an embedded etcd, and it's the timestamp oracle. Timestamps are used in TiDB, and they get assigned to data, and they get assigned to transactions. And this is how the whole MVCC system works, to make sure you see the right data for your transaction. So these timestamps are quite important. The placement driver also takes care of the placement, so where a specific piece of data is placed. This is taking into account the labels of the machines, which can be like the availability zone or other properties. This is to make sure that, like, if we have like 3 copies of a specific set of data, that these 3 are all placed in different availability zones, to make sure that any of the availability zones can fail without causing any interruptions in the cluster. The placement driver is also making sure that we split bigger data regions, merge smaller regions. It's trying to see that, like, maybe specific data regions are more hot, and that they are not all clustered on a single machine, but like spread out to the whole cluster, to make sure that both the load is spread out and the capacity is spread out over all the available machines. So the next part is the TiDB server. This component is written in Go. Both the whole platform is called TiDB, and this SQL node type is called TiDB. So two names for the same component, basically, which can be a bit confusing, but that's just how it is. So this is where we implement the MySQL protocol and the MySQL syntax. So that's what the application is talking to. And this then knows how to access the TiKV nodes to fetch the right data, or the TiFlash nodes to fetch the right data. The TiDB nodes are stateless. It doesn't really store any data. It might store some like temporary data, but not anything permanent, because the permanent data is all on TiKV. So TiKV is a key value store. This is a Cloud Native Compute Foundation project. We donated this to the Cloud Native Compute Foundation, but we're still maintaining it. So database tables are stored with a row ID or a primary key, and then the columns are stored as value. As an end user, you don't really notice this. You don't really see it. It just looks like a regular MySQL. So the fact that it's key value, that's nice to know if you want to look at the inner workings. But from the application standpoint, you don't need to care about that at all. So now we can look into the TiDB architecture a little bit more. So let's say we have a table called orders with like thousands of rows, and each row has like an ID and a few columns. And then we might want to run an SQL query on this table. So the query is select ID from orders, where ID is and then like this big ID of like, I think 1,000,001. If you look at the table in the bottom left corner, you can see that this ID 1,000,001 is in the red portion of the table, which is stored in region 3. So if we send this SQL query to one of the SQL nodes, in this case we're sending it to TiDB node 1. This knows how to like which ID is in which region, because this is being cached, because this is coming from the placement driver. So it knows that for this specific ID, it needs to contact region 3. And region 3 is on TiDB node 1. So that's where it will fetch this data from. Of course, then this data is not only stored in like one machine, but it's also stored in the two other availability zones on node 2 and node 6. So there are like 3 copies of the data. One is the primary copy, and that's what the TiDB node is using to run this query. The important thing to note here is that like we now show like 3 regions per node. In practice, like you will see like thousands or millions of regions per node, because like there are just 256 megabytes, and your total data size is probably like multiple terabytes or petabytes. But that doesn't really fit on the slide very well. And because of all these regions are distributed, both the leaders are distributed and all the other copies are distributed. That makes sure that like all the nodes are used roughly the same amount for roughly the same amount of queries. So there's not a single primary or a single leader. This is also true for the SQL layer. It doesn't really matter to which TiDB node you're connecting. So looking at one of the next things with that can be a problem with MySQL, scalability. So in MySQL, all the writes, of course, go to the primary, and all nodes store a complete copy of all the data. So what if you want to scale for more reads? Well, you add more replicas. That's kind of easy, and that's what the whole internet has been using for like many years for all the big websites. But what if you want to scale writes? So you want to be able to take more writes. Well, you replace the primary machine with a bigger machine. That might work for a bit of time, but then also you need to make sure that all the replicas are replaced with bigger machines, because they might get promoted at some point, and you don't want to just like get less capacity because the promotion happened. So what about scaling data volume? Well, you increase the disk size, but you cannot just increase the disk size for one instance. You need to increase the disk size for pretty much all the machines, because they all have a full copy of the data. And what if you want to scale reads, writes, data size, and maybe you want to scale the data size to more than what a single machine can really work with? Well, then you need to start sharding. So you get just multiple setups, and then the application needs to decide where which customer is living. Um, this might work quite well in the beginning, but resharding is usually quite a difficult thing. Getting analytics right with the sharded setup can be very difficult. And you can always have situations where one shard is way more active than all the others. And so it's really difficult to balance all the data and queries over all the machines efficiently without getting hotspots anywhere. So of course, with TiDB, we are thinking that we have a better way of doing this. So basically, for all the things that you might want to do with a cluster, the answer is always to add more nodes. So you want to scale reads, writes, data volume, you just add more nodes. So the TiDB nodes, those are used for serving queries. So if you want to be able to serve more queries per second, or you want to be able to have more connections from your application, you just add a few more TiDB nodes. If you want to store more data, you add more TiKV nodes, because that's the primary storage of all your data. And the cluster will automatically balance all the data over the new nodes as well. So this is the same picture that I showed before, showing the basic architecture of TiDB with the query that we saw before and the table that we saw before. And now let's see how this looks like if we are going to scale up the cluster. So we add more TiDB nodes. So this is just adding a node, putting it in your load balancer or in your application configuration, and you're good to go. And then we added 3 TiKV nodes. And what now happened is that the nodes has joined the cluster, but the load is the capacity is not distributed evenly, because the new nodes don't have any data, they don't have any leaders, they don't have any copies of anything. So now we need to actually distribute the data again. This will be done by the cluster without any manual steps. And now the data is distributed over the whole cluster, and you can add more data. If the regions get too big, they will split automatically and you get more regions. And if your disk is starting to get full again, you can just add more nodes again. So this makes it a very scalable solution. So what I explained before is that the TiDB nodes are doing the SQL processing, and then the TiKV nodes are used for storage. But we made this to be a quite intelligent storage node. So the TiKV nodes can be used also for the push down of queries. So if you have a query like a count star from a table with maybe a where condition, what we can do is to actually push the count star to all the individual TiKV machines, including the filtering. So the TiKV machines can filter the right rows, get the count star for each region. Then the per region results get sent to the TiDB node. The TiDB node combines these things, and then it will be sent back to the client, and it will just behave the exact same as like the query would have behaved with a single instance database. But the big difference is that now you have way more resources and you have to send less data over the network. which can be really helpful to get some good performance, especially with like really large data volumes. So in TiDB, we are storing data with a key value format. So the application just sees normal tables with rows and columns. And then on the storage layer, you're seeing just a key value instance with the key being the ID of the table, an ID of the row, and then all the columns of that row will be the value, basically. So for normal rows, this is just the ID of the table, ID of the row. The ID of the row is often the same as the primary key. This doesn't have to be the case. If the primary key is not used directly, there will be a generated row ID, and then the primary key will just be an index, basically, that links the real primary key to the generated row IDs, but that's not the default. And for indexes, we are basically doing the same with like a table ID, an index ID, and then the actual values that are being indexed. So a small example of how this looks like. So we have a table called user table with a name and an email and a ID that's a primary key. We can see that there are like 2 rows of this table. And then in the TiKV, we have the ID of the table, in this case 101, and then the ID of the row, which is the same as the primary key. And then we have the values of the columns of the table. If we now add an index on the name column, then like the table itself still looks the same, also in the TiKV. But then we get a few extra rows in the key value store with the index ID of 1 for this table 101, and then the values that are being indexed. So within a TiKV node, there might be like multiple regions in a local RocksDB instance. RocksDB is the LSM tree that we are using for TiKV. So these regions are all 256 megabytes, and they're stored locally with RocksDB. And then each data region is a raft group with 3 replicas. So basically, we're combining RocksDB with raft to get a high available setup with an LSM tree. So if we want to scale out things, like let's say we have three nodes and they start to become a little bit too big, then we need to split this region 1. So then like it's split into 2 regions. This is the easy part. And then like what we can do is to rebalance things by adding another machine that might already be part of the cluster, adding an extra copy to this second region, removing 1 copy, and now we are distributing things through the cluster. So the images that I showed before show not only TiKV, but also show TiFlash. TiFlash is an optional component. And basically what we're using it for is to improve the analytical capabilities of the database. So in many cases, you might have an application that's doing like all kinds of reads, writes, on like an OLTP database. And then there might be like an ETL job or like a data stream that sends things to like a Vertica or some other kind of analytical database. And then from this analytical database, some reporting is generated. This all works quite well, but it has a few drawbacks. So the ETL might be done either like on an hourly basis, or it might be done on a daily basis. So all the reports are basically done on older data and don't include the most recent data. The other thing is that because there are quite a few components, things can fail, and it can be fiddly to monitor and babysit all the ETL jobs and things, because these things tend to start to break if the data size increases. So with TiDB, one of the things you could do is actually get rid of this whole ETL job and just only use TiDB, both for the OLTP data from your primary application and also to generate reports. So the benefit is that the reports are using fresh data. There's no ETL required anymore, so there's nothing that can break. And this works really well, especially when it comes to like real-time dashboards to actually see what's happening right now and allow you to like monitor things. In some cases, you might still want to do like a full-scale OLAP system, especially if you want to sort data in a different way that's easier to query for reporting. But for a lot of like dashboards, etc., this works really well. So TiFlash stores one or more copies of data that's already in TiKV, and then stores it in this columnar format on TiFlash. So it's always storing a copy. It's never the primary storage. And it's based on a heavily modified version of ClickHouse. And one of the special things is that this joins the Raft group as a learner. So it will directly get the same data as the TiKV machines. And because it's working with the same timestamps as the TiKV and the transactions, it's made to be fully consistent. And this allows the optimizer to choose TiKV or TiFlash for a query or a part of a query where this makes sense. So if you have like two tables and only one is available in TiFlash and you're doing a join, it might still be able to use TiFlash for a part of the execution of this query. And because the durability is guaranteed, the result is the same as if all the things were just only coming from TiKV. So you don't have to like choose to use TiFlash when you're doing the query. There are options for query hints and a few other things to set whether or not it should be using TiFlash or not. But those are mostly for like troubleshooting, debugging, or maybe to like preserve the resources of TiFlash for specific applications. So this is basically what a cluster looks with TiFlash. So we have the data in region 3 stored like 3 times on TiKV, but then there's a copy on TiFlash. And this allows you to run queries on TiFlash for like the columnar storage. So it's a different way of storing it. And one of the things also to note is that like if all your TiFlash machines would fail, you can always rebuild the data from TiKV because it's the exact same data. On this image, it only shows like one copy on TiFlash, which is not something we normally recommend, but we always recommend multiple copies, but that doesn't really fit well on the slide. One of the other interesting properties of TiDB is what we've done with schema changes. So if you run a schema change like a alter table, and maybe to like add a few columns, drop a few columns, add or remove some indexes, or change like the data type of a column, these things can be disruptive in other databases where it might need to take like a metadata log for doing this, and this might have impact on the actual application that's running. So you might need to schedule like a maintenance window for this. So because this is quite painful, like in MySQL, there have been external tools that can help you to do this in a more efficient way. This is both PT Online Schema Change and GitHub Ghost. So these basically do the same, but then like they create a new table, they apply the schema change to the table, and then start copying data in the background in a smart way. So this works really well, but it's not very efficient because you need to copy the whole table only to add like one column, for example. In MySQL, they started to make more of the schema changes online, where like MySQL itself is able to provide like a online option for many things like adding indexes and trying to do things with the metadata only where possible. But there are still quite a few things that require like a table rebuild or other things that might be disruptive to your application. So in TiDB, everything is online. Metadata only changes are done where possible. And this also allows you to just work with ORMs and like run your database migrations in the way that your ORM wants to do it, without having to like resort to like third-party tools. We also are using our distributed execution framework to do these schema changes, especially for like adding indexes. So instead of doing this only on a single node, this is split into like smaller tasks. These tasks are distributed to multiple machines and run in parallel on multiple machines. And this makes it really fast to add indexes on like larger data sets. And like the online schema change option is like a really popular thing in TiDB, because it's a lot easier than the external tools, and really allows you to like roll out application changes when needed and not have to like wait for like a maintenance window or all kinds of other things. So TiDB is open source, and that also includes like many of the tools that we have, or like all the tools we have. So you're getting the database, but you're also getting like a fast backup and restore option. So what we have done with backup and restore is that we backup to S3, we restore from S3 or compatible system. And basically every TiKV node is making its own backup. And because they are all streamed to shared storage, this is how we can make the backup consistent based on the properties of like the RocksDB LSM tree. And then we can also restore quickly by restoring all on the machines in parallel. This also means that if your data size like triples, you also add more nodes, and it also makes sure that your backup capacity improves quite a lot with if you add more nodes. One of the some of the other tools that we have is dumpling, which is a tool to dump data from MySQL or other compatible databases in SQL or CSV format and do this in parallel. And this allows you to like do a quick dump and a restore if you want to like dump data from MySQL and load it into to TiDB. The loading itself is done by Lightning. This is doing this in a smart way by doing it both in parallel and trying to actually build the SSD files for TiDB locally and then just sending them to the server and importing those directly, which is a lot more efficient and a lot faster than having to send all the SQL queries to the TiDB layer. We also have data migration. This is a tool to binlog-based replication from MySQL, MariaDB to TiDB. It's made to be high available. And we have change data capture. So this allows you to export data as a data stream from TiDB and send this as like events to Kafka, to MySQL, to like a TiDB cluster in a different cloud region, for example. And this is being used mostly with Kafka to like feed other applications or data warehouse applications that want to know what's happening in the TiDB database. TiDB also includes dashboards. This includes a few Grafana dashboards with all kinds of graphs because all the components are basically having like built-in metrics. We also have a TiDB dashboard for statement history and many other things. So this is what the TiDB dashboard looks like. You can see like a graph with some CPU time and then all the queries, and you can also like look at slow queries, see like what execution plans were used for queries. And normally you would just see these things mostly in like enterprise offerings of databases, but this is also completely open source and included by default. We are using RocksDB, and because RocksDB is using an LSM tree, this makes it way easier to actually show multiple versions of a table. So this allows you to do time travel. So data in TiDB are never actually removed directly. It's always garbage collected later. So basically, what you can do is to set a TiDB snapshot variable to like the specific date and time that you want the data, or like add the date and time of the data you want to the select query or to your transaction. And if this is within this garbage collection lifetime, the database is actually able to do this. So if you want, you can just say like, what did my table look like 5 minutes ago? It will show you the data of the table from 5 minutes ago, including any schema changes. So if you drop the column and then look back to like just before when the column was dropped, you will still see the column. And by default, the window in which you can like see all the versions is like 10 minutes, but you can also set this to like hours or days. And then you can see like way more versions of the table than just only the last version. It also has drawbacks. Of course, if you have like a large table and you want to free up some disk space, and you have set the garbage collection lifetime to like 24 hours. Well, after dropping a table, you need to wait 24 hours before this data is actually being freed. But this can be quite a useful option. We have also built in a built-in flashback statement that allows you to recover the last version of a table or a whole schema or a whole instance. So basically what this does is after dropping a table, it just goes back to the last version of the table and restores that last version of the table, which can be really useful if a tool or a person might have dropped the wrong table by accident. It's not a full replacement for your backup, of course, but it can be really useful. We also have some limitations. So we try to be compatible with MySQL 8.x, so 8.0 and 8.4. We try our best, but of course we don't do everything exactly the same. We have a row size limitation that's limited to 120 megabytes. And there are quite a few features that we don't support yet, like triggers, stored procedures, events, XML functions, geospatial data types. But this list used to be a lot longer, but we've now implemented foreign keys that we didn't used to have. And also we are now working with like full text search options, and those are available in our cloud offering and should be landing in our normal product as well. So to conclude, TiDB is compatible with MySQL, and it allows you to do easier scaling. It has high availability built in by default. And I would say it's more developer friendly because you don't need to care for like read-write splitting. You don't care about like replication delay. That's like the data you just wrote might not yet be readable. So we don't have the replication delay in TiDB. And there's no need for manual sharding or like specifying sharding keys with your query. So this makes it a lot easier for developers to work with your database because it just looks like a normal, regular database, and they don't need to care that it's a distributed database. And the online DDL and quite performant DDL, I think is also a very useful thing for developers because this just allows them to roll out changes more easily and also faster, even if the size of the data is increasing. So that's my last slide. We are available on GitHub. We have a Slack instance in case you have any questions later on. And if you want, you can try TiDB locally with a tool that we have, TiUp. This spins up like a complete cluster on your machine so you can see what it is. And on TiDB Cloud, we have a free tier. And if you want, you can also deploy in Kubernetes, if that's more of your thing.
Hi, Daniel. First of all, great talk and nice to see you again.
Thank you.
As Daniel mentioned, please ask questions in the chat if you want to. In the meanwhile, actually, I have a lot of questions, but I will try to limit myself because time is limited. First of all, I was curious about isolation levels of transaction. Do you support all transaction levels? And if so, are there differences between TiDB isolation levels and MySQLs?
So we only have a single isolation level that we support. I think it's quite similar to repeatable read in MySQL. There might be a few small differences. The exact description of that is available on our website. Yep.
Okay. Another question I have, you shown the architecture, you shown you have availability zones. Can you explain how replication between available zones happen?
So if you have one data region, so a piece of 256 megabytes, there are like 3 machines that are on which these 3 members are. And then Raft is being used for the replication of data. So Raft does 2 things. It elects a leader. That's the primary. That's where the writes happen. That's where most of the reads happen. And then there are 2 replicas. And Raft also takes care of the sending the data to the other members.
Okay, and is it synchronous or
Yes, it's you could say it's synchronous. Yes.
interesting? Do you you mentioned you aim to be compatible with MySQL 8.
Yes.
Do you also pay attention to some MariaDB specific syntaxes, or?
Yeah, so MariaDB does a few things different, and we also have our own differences with MySQL. We try to support what makes sense, and one of the examples here is sequences. So we implemented sequences. MariaDB implemented sequences. MySQL didn't. So there we are following the MariaDB syntax, and there might be a few other places where we have MariaDB compatibility, or also there are a few places where we have Oracle compatibility.
Yeah, great. Another question is about the sharding, because you said that you don't have to care about sharding keys. But if I want to, do I have a way to control which data is where?
Not really. So normally the primary key is being used as the ID of the row, and that's on which we do range-based sharding automatically, basically. So if you're using a non-clustered primary key, then the primary key just becomes an index, and there's a generated row ID. So that's one of the differences that's possible, but otherwise there's not really that much that we allow people to do.
Okay, I see. But more specifically, if I have some small tables that are often joined with basically any other table, do I have a way to make them redundant across different regions?
So you're saying that you want to have a few different tables that you want to join together very often, so you want them to be on the same machines?
Not really. I mean, suppose I have small tables that are often joined with other bigger tables. To avoid cross-region joining, do I have a way to say, okay, this table should be in every region?
So we have a cached table option. So for tables that are small, mostly red, we have the caching feature where the tables are basically cached on the TiDB servers. So that helps in many of these cases.
Great. Okay, last question from me, but I hope that someone else asks another question. You mentioned the time travels. I'm curious, can I join the data as it is now with data as it was in another point in time?
No, that's not something that we allow. So like you could of course export data because, for example, dumpling also allows you to specify from like which time you want to export. Or you could create some new data based on like a select query. But there's not any option to like combine different data from different times for different tables in a single query.
Okay.
It would be interesting.
Yeah, it's something that you typically can do with temporal tables with the databases that support them.
Yeah, it would be interesting to see like a diff of like two versions of the table to see what changed.
Yeah. Oh, well, actually, I do have another question that just came to my mind. Recently, I tried to figure out the best ways to select random rows with different databases. How would you recommend to do it with TiDB?
So you want to, I guess you have like a big table and you want to like pick a few rows randomly, right?
Yeah, completely random.
Yeah. So the feature in SQL for this is called table sample. I think Postgres supports it. We support some of it as well, and a few other databases might support this. And this is way better than like the thing that you might do with other databases where you do a select and then order by random, because that's usually not very efficient.
Yeah.
And like a table sample is usually way more efficient.
Yeah. Great to know that you support it. Okay, I don't have any other question, but if someone has something to ask in the next minute, I'll be happy to ask Daniel. Okay, by the way, it was great to listen to your talk, and thank you very much, Daniel. And thank you to the attendees, of course.
Yes.
Yeah, please.
Thank you very much for allowing me to speak, and thanks everyone for attending.
Great. Just to let you know, the next talks will be, well, on stage one, we will have Emmerich Ingo talking about interesting database ideas you might want to pay attention to. And on stage two, we'll have Christian Pretorius, author of the Bark database, talking about Bark and ordered level 1 plus level 2 distributed cache. So after a coffee break, you will be able to attend these talks. Thanks again to Daniel and everyone else, and see you all at the next talks.